Okay, we're going to finish up this section talking about quadratic equations, functions, zeros, and models. So we're going to look today at what does the discriminant tell us, some equations that we call reducible to quadratic, and then also talking about applications. So the first thing I don't want to spend a whole lot of time on this, but there is a part of the quadratic formula that is quite important, because if I just look at this one part of the quadratic formula, it can tell me a lot about the possible solutions. And so remember the quadratic formula, opposite of b plus or minus the square root of, right, b squared minus 4ac all over 2a. So x equals that. Don't just, I really hope you understand that the quadratic formula gives me the solutions. It tells me what x would be to a quadratic set equal to 0. Okay, so understand what that quadratic formula gives you. It gives you the solutions to a quadratic set equal to 0. Okay, what are those solutions? I want to put x equals. I don't just want numbers floating around. I want to put, x equals those numbers. All right, so when I look at the quadratic formula, the discriminant is going to be this part right here. And you may have heard that term before. But the discriminant is going to be what's under the square root. And what that does for us is it tells us basically what type of solutions we're going to have. So the discriminant is this b squared. Hold on. Sorry about that. So b squared minus 4ac. That's what we call the discriminant. And the discriminant, a couple things. So if the discriminant is equal to 0, so if I take b squared minus 4ac and it's equal to 0, then we will have one real number solution. And you can kind of see that numbered. Hold on, let me finish writing. One real number solution. Look at, if my discriminant is 0 right here, then all of this is gone right here. And what is my solution? It's just negative b over 2a. So I don't want you to memorize like, oh, what is my solution when I do that? You would just do the quadratic formula like normal. But the discriminant, it's a nice way for us to just look at a quadratic and know what's going on. So if that's 0, if there's only one real numbered solution, then I have a quadratic that maybe comes down and grabs the x-axis somewhere and comes up, or maybe comes up and grabs the x-axis and goes down. That's going to be the type of graph that I'm going to have for that quadratic if I just have one real solution. Okay, so it can equal 0. It could be positive. So if this guy is positive, okay, if it's positive, then we have two distinct or different, right? Two distinct real numbered solutions. And you can even get into, I'm running out of room here. I don't know what that, I'm trying to abbreviate solutions and it's not working very well. But if this is a positive number, then I have plus or minus the square root of a positive number. I'm going to stay in the real numbers. You can talk about if you're going to have rational or irrational solutions based on if you have a perfect square or not. But we're just talking about the nature of our solutions. And then the last one is, well, this guy could be negative, right? So what if this guy was less than 0? Then we're going to have two distinct, two different, not the same, obviously, imaginary number solutions, right? Because there's going to be an I involved. Imaginary numbered solutions. I'll let you put solutions. And so if I have, like 5 square root of negative 25 and I have 5i, and they're going to be complex conjugates of each other as well, because I won't be able to really simplify it. I won't be able to combine it with that negative b. So I just want to let you know about that. That's what that's kind of what the discriminant kind of tells us. For example, if we wanted to describe the nature of the solutions to x squared plus 5x plus 8, or if I wanted to talk maybe about the zeros of this function, I could just look at the discriminant. So b squared minus 4ac in this case is going to be 25 minus 4 times a is 1 and c is 8. So I get 25. Oh no, I'm going to have to do simple arithmetic in my head. I get -7. So what does that tell us? That tells us that this guy right here has two distinct imaginary numbered solutions. Also means it doesn't cross the x-axis because we don't have real numbered zeros. Okay, just want to point that out. We're not going to spend really any more time on that than that, because that's about it. All right, so let's talk about two more things, remember, in this section to talk about. One second to last thing are what we call equations reducible to quadratics. And I'm just going to do a bunch of examples for you here. Not a bunch, but a few. What's a few? My daughters always ask me that. What do you mean by a few? I'm like, I'm not sure. A few minutes? A few more minutes on the iPad? I don't know. Suspense. So what we mean by equations reducible to quadratics is, can I make a substitution to make an equation that kind of looks like a quadratic but maybe isn't of degree 4? Could I mess with it a little bit to make it look like a quadratic so I can use the quadratic formula, or I can factor. I can use those tools that I have that I can solve quadratics with. I can use those tools to solve maybe something like this, which is a quartic, right? It's degree 4. So the trick here is going to be realizing that x to the 4th could be written as x squared squared, right? We multiply exponents when we raise an exponent to another exponent. So what I'm going to do here is I'm going to make a substitution. I am going to let u, or m, or whatever you would like to use, let u equal x squared. Okay, now why am I going to do that? You're like, Sarah, you're crazy. Why are you doing that, Sarah? Well, watch what's going to happen. You guys, this is just hilarious. It's just a kick. Look at what happens here. Those x squared, so remember I'm letting u equal x squared. So this x squared right here is going to be replaced with a u. So I get u squared. This x squared here will be replaced with a u. Just get plain old u then, equals 0. And if you notice, yay, we have a quadratic, right, that I can factor. I guess you could do the quadratic formula, but you guys, you should really try and factor. Don't be scared of factoring. It's going to save you a lot of time if you don't have to do the quadratic formula every single time you see a quadratic. So look at that. I can factor this guy. So I have, when I set that equal to 0, I get u equals 1. When I set that one equal to 0, I get u equals 4. And now I didn't start off with u's. I started off with x's. So we need to come back to what our original substitution was. So the poor u, we just use it and then we throw it away because we actually don't. We just use it to get where we want and then we throw it away. So what are my solutions? X squared equals 1, so x would equal plus or minus 1. Remember, whenever I bring in a square root, I need to bring in a plus or minus. So I have 4 solutions to this. I have x equals -1, 1, -2, and 2. So if I graphed this function actually is pretty cool when you graph it. We'll talk about graphing these kind of later, but my y-intercept is going to be 4, right? 1, 2, 3, 4. And what this does is it kind of comes down, comes up like this. Whoa, I was doing so well. Comes down and goes like that. So if you notice, we'll talk about this later in this class, but the end behaviors, like the sides of my graph here, are similar to a parabola, and that's because of the even exponent here. And then it crosses in 4 spots. So what are my zeros? My zeros are -1, or -2, -1, 1, and 2. And that's what we mean by an equation reducible to a quadratic. It's an equation where I can make a substitution to make it look like a quadratic equation, and then I can use the things that I know how to solve a quadratic with. I can try and factor, can do other stuff like that. Let's look at another example that, because these can be kind of tricky. So if it's raised to the 4th, hopefully that's pretty obvious, but one like this is a little harder. Let's look at one like this. So 2x minus 9 root x. This one's not as obvious, I don't think, as to what the substitution is that I'm going to make. But what you want to remember is that a quadratic is of the form ax squared plus bx. Well, let's not use x's. Let's say if I make that substitution with a u, it doesn't matter, right? AU squared, sometimes we call those dummy variables, like it doesn't matter which variable I use, it just represents a variable. So I want to get in this form, AU squared plus BU plus C. So one trick is to notice that whatever I'm going to let u be is going to be that middle term right there. So my guess here is that I'm going to let u equal root x. Now, what's going to happen when I square it? So let's look at that u squared. If I square both sides, notice what is u squared? When I square that square root, I just get x. Isn't that cool? Another way, I love doing these. Another way to think of that is this is 2 times the square root of x squared minus 9 root x plus 4 equals 0. So I don't know why my green kind of went a little dark there. So when I substitute here, this guy right here is just going to be u. So this is u squared minus 9u plus 4 equals 0. Now we got to factor this guy. You know that you can factor by grouping, that trick where you do 2 times 4 is 8, and you find two numbers that multiply to be 8 but add to be a negative 9. That'd be a negative 1 and a negative 8. Let's rewrite that middle term then as a negative u minus 8u plus 4. Or you can, if you can see how to factor this, of course, just factor it, right? Kind of using that guess and check method. Minus 1, what can I take out of these two? A negative 4. So I'm left with, oh no, I'm not left with 8. Oh my goodness, how embarrassing. Not 8. I'm left with 2u minus 1 equals 0. And then I'm going to factor out that 2u minus 1. So 2u minus 1, what would I be left with if I take that out? I'd be left with u minus 4 equals 0. Okay, so what are my possible solutions, right? Well, I have 2u minus 1 equals 0, or u minus 4 equals 0. If I choose u's that make either one of those 0, my whole equation is going to be 0. So let's see what happens here. So I get either u equals 1/2, right? Or I get u equals 4. But remember, I didn't start off with u. I started off with x. So I'm going to come back to where my initial substitution was. And then I'm going to say, okay, the square root of x then equals 1/2. Remember, that square root's already there, so I do not need a plus or a minus, you guys. That square root has already been given to me. Remember, the only time I bring in a plus or a minus is when I bring in a square root that was not there originally. And now how do I get rid of the square root? I'm going to square both sides of the equation. So what are my possibilities, or what are my solutions for x? If I square 1/2, it's 1/4. If I square 4, it is 16. So I have two solutions. Those two solutions are 1/4 and 16. Hope that makes sense. Does that make sense? Hope that makes sense. Good. So kind of look at that. There are other ways, that you can make substitutions, but that's what we mean by substitution with the quadratic. What you want to do really is just look for that middle term, and whatever you can make your u be here, then see if when you square it, you're going to get that first term there. Okay. All right. And then the last thing I want to do are just some application problems. So applications with quadratics, we're going to, in the next section, see how I can find maximum and minimum values of quadratics, and that's what we call optimization of functions. But in this case, we're just using applications. Okay, so we're going to look at some problems that involve quadratics when we solve them, I guess is how we can say it. So I'm going to kind of steal a couple problems out of the book. Okay, so first example. At 630 feet, the gateway arch, and I'm going to have to give you a function here to be able to complete this, but the gateway arch in St. Louis, I've seen it. I've never actually been in the arch. Wasn't that in a Spider-Man movie or something a while ago? Anyway, is the tallest man-made mountain in the United States. Tallest man-made monument in the U.S. This is information that we don't actually need to solve this problem. However, let's just write it down. How long will it take? An object How long will it take an object drop from the top to reach the ground? Now, here's the thing. Let's finish writing. Let's hope that there's no one underneath where you are dropping this object. Let's hope this object isn't anything super fragile or valuable. And here's the other thing we have to do. We have to live in perfect math world, you guys. So I laugh in perfect math world, which is a world I love to live in perfect math world, for now, we're not going to worry about pesky little things like friction or air resistance. So I'm not talking about dropping a feather, right? I'm just talking about dropping something, and I'm really just concerned about how gravity is acting on that thing. So there is a formula that we need to use, and this is a formula I would give you. The next examples I'm going to give you are not going to be this formula, but what this formula gives you, so this S equals 16t squared. This guy here approximates the distance. The distance S, and this is in feet. If you know anything about acceleration due to gravity, you can kind of see if that was like a 9.8 or 4.9, then I would be in meters. This is going to be in feet because it's 32 feet per second squared is acceleration. So approximate the distance S, right, in feet that an object falls freely. So we'll just say object falls from rest in t seconds. So part of understanding how to do a word problem is getting your function or your equation and understanding what this equation is going to give you, right? So if you look at an equation like this, what does the t stand for? The t is the seconds after you drop the object, right? And after so many seconds, what the s gives you is actually the distance that object has fallen. It's a pretty basic formula. If you've taken any physics, you'll see this. If you take calculus someday, you'll see a formula a little more complicated than this, but pretty much the same. But this is the formula that's given, and let's see what this whole thing is asking. So at 630 feet, the rest of the stuff doesn't matter at all to my problem. How long will it take an object dropped from the ground to reach, or dropped from the top to reach the ground? So a lot of times what I like to do is I like to put down, what do I want? I want to know t, right, when, and what is given. S, what is given? Given is the height from which we are dropping this object. So if I can figure out that, if I know what I want and I know what I'm given, then I can plug this in. So that means I'm just going to do 630 equals 16t squared, right? I know I want to plug in the 630 in for S because S is not time, S is height. So I want to do that. Hold on, I'm grabbing my calculator. 630 divided by 16. So I'm going to divide by 16, right? You get 39.375 equals t squared. Now, I know I have been saying quite often that whenever you bring in a square root, you need to bring in a plus or minus. However, I also want you to think and use your mind and think about, does a negative make sense in this case? I don't know. If you figured out how to go back in time, I need you to contact me and we need to write a paper or something. But we can't go back in time, so we're just going to do a positive 6.275 seconds. And of course, you're going to write your answer in a sentence, right? It will take the object approximately 6.275 seconds to reach the ground. And again, what do we do there? We square rooted. Okay, so that's a pretty easy application, I think, especially because the function is given to us. Sometimes when you get these applications where the function is not given to you, that's where it can be a little bit tricky. So let's go ahead and find one maybe that's a little trickier than that, so we can do one that's kind of more interesting. So we'll do 2 more application problems and then we'll call it good. All right, so how about this one? One number, okay, is 6 less than another. Okay, one number is 6 less than another. The product of the numbers okay, is 72. I love problems like this. I think they're so fun. Find the numbers. Now, I understand that you could mess around with numbers and figure out what these two numbers are without doing any algebra. However, I do not teach mess around with numbers class. It's not a college level course. I teach college algebra, and so I expect you to use algebra to solve this. I will even put on the directions on like an exam, it will say use algebra to solve the following problem. If you don't use algebra, you don't get credit, okay? So let's go ahead and define some stuff. Just like we did before when we talked about solving systems of equations, I'm gonna let x equal one number, right? And you can do y equals if you want to, that's fine. Or you could just say x minus 6 is the other number. This is very scientific here. One number, the other number. So I need two equations that relate these. Doesn't matter which one we do here. One number, oh, I guess the way I have it written is I should go with one number, that's what I've defined x to be, is equals 6 less than the other number. It's not 6 minus y, it's y minus 6, right? I want to make the other number smaller. And then what else do I know? The product of the numbers is 72. So product, remember, is multiplication. Okay, so I get this equation in two variables, two equations and two unknowns, and I can do substitution. You also could have probably gone straight to x times x minus 6 equals 72. I would accept that also. But the way I have it here, I'm going to actually work in y's, so I'm going to plug that in. So I have y minus 6 times y equals 72. I'm going to take the y through, so I get y squared minus 6y. Bring the 72 over because I see I'm working with a quadratic, right? Now I'm ready to go. So I'm going to factor this guy. It looks like it's y minus 12 times y plus 6, I think, equals 0. Okay, so look at, I have two possible solutions. I have y is either going to be 12 or y is going to be negative 6. Remember, the problem didn't say that my solutions have to be positive. The problem didn't say anything about what my solutions have to be. It looks like I have two sets of numbers that are going to satisfy this, because what is x in this case? It's 12 minus 6, which is 6. Sure enough, 12 times 6 is 72, and 6 is less than 12. Likewise, if I put this in here again, negative 6 minus 6 is negative 12. Sure enough, negative 6 times negative 12 is positive 72, and negative 12 is 6 less than negative 6. So we have two solutions to this problem. We have the solution of 6 and 12, and then negative 6 and negative 12. Again, you'd state that in a sentence. The two numbers are 6 and 12, as well as negative 6 and negative 12. Okay? I don't know if it's easy. I hope it's pretty straightforward with the work we did with the two equations with the two unknowns. Again, I really need you to use algebra to do this, okay? Really, really, really need you to do algebra to do this. All right, let's look at one other one. This is a classic one, and then we'll call it good. Okay, one more example, and you've probably seen these before. Like, you can actually take a piece of paper or a piece of cardboard and do something like this. I love doing these. An open box is made from a 10 centimeter, okay, by 20 centimeter piece of tin, or I guess you could get a piece of tin. I wouldn't recommend that. You're gonna cut yourself, at least not just to look and see what is happening here. Piece of tin by cutting a square from each corner. And folding up the edges. I'll draw you a picture. It would be easier if I could just like show you using a piece of paper, but I'm not going to do that. So, all right, the area. So again, let's see what we know and what we want, but the area of the resulting base. Okay, is 96 centimeters squared. What is the length of the sides of the squares? Is the length? I said it, but I'm not writing it. What is the length of the sides of the squares? We might have to use another page on this one. So this might be a problem you've seen before. It can be a tricky one, but here's the idea here, okay? So what I'm gonna have is I'm gonna have a rectangular piece of tin or paper or whatever you wanna think of it as. I know that this side here is 10 centimeters, right? I know this side is 20 the way I've written this. And what we're going to do is we're gonna cut out some squares. I'm gonna just cut out these squares on the edges of the paper, okay? And then I'm gonna cut that out, and then what's gonna happen is once you cut that out, you're gonna have this kind of funny looking little rectangle thing here, and I'm just gonna fold just that part. So remember, I've cut that out, so this is gone now, okay? This is gone. I've cut those pieces out. Oh, look at that. This is great. Cut those pieces out, okay? And now, once I've taken those out, I am going to fold this up along these dotted edges. Go ahead and do it. Make yourself a nice little box. I do it with my kids all the time. Let's make a box. Great. Get some tape. I'm going to take this edge right here. I'm going to fold it up, and we're going to, get some sort of, ooh, look at this, you guys. Look at my picture. Do you see it? Do you see the 3 dimensions? I know I'm pretty amazing. See my 3 dimensions there? Ooh, look at it. I can even erase. I know I'm probably getting a little too excited about this, but that shouldn't surprise you anymore. So I'm not great at this. I tell my Calc 3 class, my poor Calc 3 class, when I teach Calc 3, it's like all 3 dimensions because we're looking at XYZ plane, and I tell them it's a lesson in imagination because I can't draw very well. That's all right. All right, so let's see what we know. So I know this is 10, this is 20. The whole thing is 10 and 20, right? And then I know the area of the base is 96. So I know that this is 96 centimeters squared. So what do I want? I want to find x, right? I want to find x. Oh, I haven't defined x yet. And what am I going to define x to be? These little squares that I took out here, I'm going to define x to be the length of one of those squares, okay? So let's look at, I'm going to actually draw these squares back in, and let's look and see if we can figure out how to determine, I'm going to have to use this fact that they give me, it's 96, right? I'm going to have to use that fact. And now what do I know about the area of this rectangle right here? Well, the area is going to have to be length, right, times width. And so can I find some sort of equation to describe this length and the width of this area here that's 96? Well, yeah, I can. I know that this whole area, or this whole length here, is 20. So how am I going to compare this whole length with this, which is 20, to just this side right here? Well, look at this, you guys. This is basically 20 without this x and without this x right here. So this side right here, I'm going to say is the whole length 20, except I'm going to take away from it 2 x's. I hope that makes sense. Same thing right here. Oh, whoa. Sorry about that. Jeez. Turn my computer off. I don't know what you just saw there, but sorry, I didn't mean to turn my computer off there. Likewise over here, right? This whole length here is 10, but I want to take away 2 of the x's. So this side right here, I'm going to describe as 10 minus 2x. And that is going to give me that area with the 96 there. And I'm going to give myself a little bit. I'm gonna get rid of my cool 3D box. I know I'm sad too. So what do we want to do? What do we want to find what x is? What are we given? We're given that the area of the base is 96. So how do I force that area to be 96? I take 10 minus 2x. That would be this side right here. And multiply it by 20 minus 2x. I'm gonna set that sucker equal to 96. Okay. So this is going to give me my quadratic. I hope that makes sense. I'm going to FOIL this out, get 200. Here I'm going to get 20x minus 40x is a negative 60x plus 4x squared equals 96. So quadratic, so I always set quadratics equal to 0 to be able to solve this, right? 200 minus 96, I believe, is 104, I think, equals 0. I think everything's divisible by 4, so let's divide by 4. X squared minus 15x, right? Plus what? 4 goes into 10 2 times, 4 goes into 24 26 times, equals 0. This one's actually pretty nice. X minus 2 times x minus 13. That's going to be my winner there. So I have two possible solutions. I have either x equals 2 or x equals 13. Guys, you got to think. I know I'm asking a lot. I get that. It's hard to think sometimes. I need you to think about your answers here. Look at what this x represents. This x represents the amount that you're taking away from each side. Excuse me. I'm taking the same amount from both sides. If I consider x being 13, that means I'm taking 13 from this side, right? And if I take 20 minus 13, I would have only 7 left. But I also have to take 13 from this side. That doesn't make sense. So I'm going to throw out that 13 because I can't actually take 13 from both sides. Try and do it on this side with the 10. You don't even have 13 centimeters to take away. So what is my solution? X equals 2 is my solution, or 2 centimeters. Again, you would state that in a sentence. The length of the sides of the squares to be taken away is 2 centimeters. All right. Hope that makes sense. Application problems are not easy. Practice, 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 practice. Do the fun sheet. Do your homework online. Let me know if you have any questions.